Okay, today we're going to talk about residual plots, the coefficient of determination, and the standard error of regression. So let's start our conversation about residual plots. To create a residual plot, we're going to take the residuals or the errors and plot these errors as distances from a baseline described by the explanatory or x variable. So we're going to look at residuals. And let's recall, what is a residual or error? This is the distance the data point is from the line of regression, which is given by this y minus y hat. It's a little off center here, but we can just make that a y hat. And remember, this just means the actual minus the predicted, or the observed minus the predicted. So remember, we're talking about the y values, or the response variable, and we're looking at these vertical distances. So we take these distances and plot them as vertical distances based on the x value. Here we are showing the graph of the points with an attached line, which shows the distances. When we do our residual plots, these connected lines will not be present. So we're seeing the lines over here. These actual lines connecting them will not be there. So you may want to use lines to get used to marking the distances if you need, and then erase them afterward to get your completed residual plot. So just remember, we're looking at, this was our line of regression. And remember these red dots are our predictions on the line. The blue dots are our actual data points. And remember, just the residual is that distance here, that this was our prediction. This is what actually happened, and they don't match up exactly, so there's some kind of error happening in our prediction here. And then what are we doing? Well, we're going to take all these values, so we can see right here, look at this distance here and say, well, we'd like to look at this as a residual. So here we have our explanatory x response y-axis. Over here, this is still going to be our explanatory x, but now this part represents the actual residuals, or the errors. So we can see that, look at this data point here. This is about this far down, and we can see that, oh, we're matching this part. Because if it was exact, right? If the data point was exactly on our prediction line, then the error in that prediction would be 0, but in this case it's not, right? So the error is below it right here, so we can see that this is the same distance as that point. This distance is the same distance as that point, and so on. So it's almost like laying this flat, but treating this as the 0 errors, which it is, and how far away vertically we are off in our prediction of the response. So what will this look like without those lines? So I'm just going to do a quick little sketch just right below it. So this point here matches up on this x value, is a little bit below. I can make a better dot than that. This one was, next one's above, below, above higher, above a little lower, and then farther below. So we kind of see that this is the same graph as this, just without the connecting bars. And this is what a residual plot would look like. And this just tells me whether or not I had an under or an overestimate in the prediction, or whether the actual was below the prediction or above the prediction. So what we do is, this one way to give us a good view of the errors, because many times we may look at a line or a curve, for instance, and we're saying, well, it looks like it's pretty good, but we can actually zoom in. The residual plot gives us a nice zoomed in view of what's actually happening and where the errors in the predictions are. So when we do a residual plot, it's just another way to get a view of how our regression line or prediction line, prediction line, or curve, because we're going to look at this with curves also. So our regression line or curve fits the data. So we're just focusing on linear models right now. So we might say that a linear model, assuming that it looks like the line is actually doing a decent job modeling the data, that a linear model would be maybe a good or a decent fit for the data when there is no pattern, distinct pattern or curve, or shape in the residual plot. This will reassures us that this linear model would be a decent or a good fit. As I said, assuming that it looks like it's a good fit to begin with. So if it doesn't look like the curve or line models the data, then there's no real reason to continue looking at the residual plots. But we still can. So if we do see a distinct pattern, curve, shape to the residual plot, this indicates that a linear model may not be our best choice of a model to fit the data. In case of outliers, we may need to remove these outliers and review our residual plot to make further analysis. Because sometimes we might want to look at it and say, you know what, it could just be a point or two. These outliers or these influential points may be causing some kind of problems with how well the curve or the line is fitting. So sometimes we might do an analysis with the outliers, and then sometimes we might remove these more extreme outliers just to see what happens. And we'll look at some examples of that later. So let's look at some examples real quick just to see what we're talking about. What do you mean by no pattern would be considered something we're looking for, and a pattern or curve is something we're not looking for? Okay, let's look at a couple of examples of some residual plots. So we have two residual plots, and one of these signifies a better fit, and the other one signifies that something else might be used to model it that would give you a better fit for making predictions with. So if we look at these two, well, we want to look for something, remember, that has no pattern. So think of it as if a line went through the data very well, then I would expect that it would hit some points, hopefully, and then you would have about equal number of points above and below, and all the way across scattered around the line. So in that case, this is what we're seeing would be a better fit. So a residual plot gives us the zoomed in perspective of the error. So remember, residual just means error. So when you hear residual, just think of error. And this line would signify like zero error. So if we had 0, like this was really close to the line, that signifies that there might be very little to no error in the prediction for this point. And down here we have our explanatory variable, whatever that will be. And there's different types of residual plots, so this is the one we're going to work with for now. So what do we want to see? If we notice how this is really kind of scattered around it. And what I want you to think of is saying, well, it's kind of above and below, right? Equally, if we look at the data, it's scattered around the 0 line, and the closer to 0, the better. So this would be a sign of a better fit. I'm going to say a better fit model, because there's different curves that we could use for modeling. Right now we're focused on linear, but there are other equations. There's many equations we can use to model with. So this is what we'd like to see. So I might call this band-shaped. Is what we'd like to see. Others you might see oval. Some might just say it's scattered. So that's really what we'd like to see. And oval means kind of just drawing an oval around this. That would be an oval shape. So I like using band, but whatever your teacher would like you to do. Now down here, what do we see? We see a distinct pattern, don't we? This kind of upside down U shape, right? Well, this upside down U, it's got a strong pattern to it. Here's still our 0, and this is what we don't want to see. So this has a distinct pattern. So we see a distinct pattern here. Distinct pattern or curve. So what does this tell us? This tells us that the given model may not be the best fit. Not be the best fit. So what's interesting when we have this is, well, we see this distinct curve here. And if we look at nonlinear models, this is actually what's called a parabola or a quadratic. And it kind of gives us this idea. So if we were looking at a linear model and we looked at the residual plot and it gave us this distinct curve, well, this would tell me what I'd want to try to use to model with the data next. So if this was a line, I'd say, you know, I'm going to try the quadratic next because the residual plot is giving me that idea of saying what to use. So those are kind of how we're going to analyze these. We want band-shaped, but we don't want to see a distinct pattern or curve. Okay, let's continue on. We're going to look at the coefficient of determination next. So the coefficient of determination. We already looked at the R value, right? The correlation coefficient. Well, if we square that value, that gives us the coefficient of determination. And this, there we go, this is the, we can say the proportion or percentage of the variation in the response variable that is associated or explained by its linear relationship with the explanatory variable when using the least squares regression line. So this is just saying, well, how much of the total variation? So we might want to put total variation in the response variable that is explained or accounted for by the explanatory variable. And here we have R squared is the explained variation over the total variation. And, well, that's just a proportion, and we will look at that later, either in another video or in class. Suppose we computed our regression line, and we are given an R value of 0.75. Calculate R squared and interpret what this means. So we need to take our R, we're going to square it, so taking 0.75, we square that value, we should get approximately 0.5625, and let's turn that into a percentage. And what does this tell us? Well, this tells us that 56.25% of the variation of the total variation in the response variable can be explained or accounted for by its linear relationship with the explanatory variable. By its linear relationship with the explanatory variable. And we'll look at an example right below this. So this tells us that 56.25% of the total variation we see, or variability we see in the response variable, can be explained or accounted for by its linear relationship with the explanatory variable. Because remember, we're looking at two variables. Our response is our variable of analysis, and we're trying to use the different variables, in this case explanatory variables, to make predictions on the response variable. And we want to know, well, how much is explained by that linear relationship. Oh, sorry, I'll put that back up. Remember, pause it if you need to finish writing this. And let's go look at an example. Let's look at this example. The following graph, the explanatory variable is describing the number of tons of paper trash, and the response variable is the number of tons of total trash. So here we have our tons of paper trash using to predict the tons of total trash. So suppose we put this into our statistical software and we get our regression line to model the data, and we're given an R value of 0.729. What is the R squared? And let's interpret this in the context of the given data. So just like before, we're going to take this value and we're going to square it. We should get approximately 0.5314. And again, let's turn that into a percentage. And what does this tell us? So this tells us that, well, look at this real quick, that we're looking at what do we mean by the variation, as we're talking about before, the variability, that, well, does the line do a perfect job of modeling the data? No, right? If it did, then every dot would be on the line. So we have this variability in our predictions using the tons of paper trash. There's this variation or variability in the tons of total trash about the prediction line. So that's what we mean when we're talking about the variation and variability. So this tells us that 53.1% of the variation in, what are we looking at? We're actually analyzing tons of total trash. So 53.1% of the total variation in tons of total trash can be explained or accounted for by, remember, what are we looking at? We're looking at a linear relationship here. It can be explained or accounted for by its linear relationship with the tons of paper trash, our explanatory variable, with the tons of paper trash. So 53.14% of the total variation in tons of total trash can be explained or accounted for by its linear relationship with the tons of paper trash. Let me just clean this up real quick. So how much is left over now? Well, if 53.14% of the variation is explained, then how much is not explained or accounted for? So we need to subtract this from 100. So this leaves, so let's subtract that. This leaves 46.86% of the total variation, or the variation unexplained. So what other variables might account for this unexplained variation? Remember, we're trying to predict the tons of total trash, and we want to know, well, how much of the variation we see here is explained by the tons of paper trash. Well, what other type of trash is out there? Well, there's biological waste, right? They're oil-based. There's metallic trash. So other types of trash may account for this missing variation in tons of total trash. And we may be able to identify every single possible type of trash, but just remember that there's always going to be natural variation as well. Let's move on to the next page. And let's look at the standard error of regression. So the standard error, or standard error of regression, that's S with the subscript of E. This measures the typical or average amount of error in predictions when using the regression line. So we can kind of think of this, relate it back to the standard deviation. So let's relate this back to the standard deviation of our data based on our linear model. So recall that standard deviation measures the average distance our data is from the mean. This is measuring an average distance that our data is from the line. Remember, we're looking at residuals, we're looking at vertical distances, the response variable. That just is just another way to say, on average, this is how far we expect our predictions to be off from what actually happens. So it is calculated using this formula. And hopefully this kind of looks familiar, right? I mean, if we recall what was standard deviation was so it looks pretty close to that, right? That's kind of familiar. Where SSE, what does that stand for? That stands for the sum of the squared errors. And we could relate this and rewrite this if we wanted to and say, well, what is this then? If we wanted to, we could write this as the square root of the sum of y minus y hat squared all over n minus 2. Let's make sure this square root goes all the way down. And I could do a little bit better with the y hat. There we go. And does this look pretty similar to standard deviation? So it looks pretty close, right? Instead of x minus x bar, we're doing y minus y hat. These are distances from the mean. These are the vertical distances from the line. And we have n minus 1 here, and this is n minus 2. Well, this was with a 1 variable. Now we have 2 variable, right? We're looking at an x and a y explanatory and response. So just wanted to point out some similarities between these two. And like before, we have technology. Technology is going to help us out a lot, so we don't have to do much calculation to get these values. So let's see how we can apply this. So let's look at the prediction. Once again, we're going to look at driver's age and their explanatory to predict the maximum distance to read a sign from in feet. In feet, let's put that in here. And suppose we use our technology and we get our least squares regression line, our best fit line to model the data, and we get this distance equals -3 times the age plus 576, and technology calculates our standard error of regression above as 51.35. So I want to attach units to this too. Now remember, we're looking at vertical distances, and what's the vertical distances we're looking at? We're looking at the max distance to read a sign in feet. So we could attach this and put feet on this. So let's write a sentence to interpret the standard error in the context of this given example. So remember that I just want you to think of this as, when you hear standard error, just think of it as average error in the prediction, and let's be a little more thorough in our interpretation. So I'm going to start off with on average, because it is an average error estimate. On average, we estimate that our prediction in the maximum, what are we predicting? The maximum distance to read a sign. So we estimate, on average, we estimate that our prediction in the maximum distance a driver can read a sign from based on, what are we basing this on? We're basing it on their age. So the maximum distance a driver can read a sign from based on their age we expect it on average to be off by 51.35 feet. So I'm going to actually say plus or minus 51.35 feet when using the least squares regression line. So on average, we just expect that the maximum distance that a driver could read a sign from based on their age will be off by plus or minus 51.35 feet when using the least squares regression line. So how do I want you to think about this? Let's put this into another view and say, well, we're looking at all these vertical distances. Remember, vertical, maximum distance. And think of this as just creating a type of window, for instance. So think of this as just saying that, well, if we looked at all those vertical distances and we averaged them out, that we can kind of create this window here of where we expect the actual maximum distance that a driver can read a sign from would fall somewhere in this window. So, and this is just looking at an average. So this is kind of an idea of saying, let's make that a little bit cleaner here, from here to here, and this vertical distance, right? This is what we mean by standard error, that on average we expect that what actually happens to be within this window of our prediction line, the blue line. Of course, there's some that are outside of it, but this is average. So we're just building a little window here. So let's continue. Let's go down and look at example 2, or question 2. Predict the maximum distance that a 60-year-old driver can read a sign from. Well, we did this already, right? We know how to. We're just making a prediction. We're just going to plug in 60. So we have the equation distance equals -3 times the driver's age plus 576. Working that out, we will get 396 feet. And that would be how far we'd predict a 60-year-old. Now, where would we expect to find an actual 60-year-old? So keep in mind, we don't have a 60-year-old, and even if we did, maybe we have multiple of them. Then which one do we use? So we just want to have an idea for an estimate on where we actually expect to find a 60-year-old based on using our standard error. So think of this, keep this view in mind, and let's go down to number 3. So using your prediction and standard error from above, how far would you expect an actual 60-year-old driver to be able to read a sign from? I'm just filling in 2 again real quick. We had this to be 396 feet was our prediction for a 60-year-old. So, well, I would expect that, remember, on average, we expect that our prediction is going to be off by 51.35 feet, right? The standard error above. And we just need to make that kind of window. So what do we have? We should do, well, if we predict 396 feet, that might be off, what? We might be below it, 51.35, or we might be above it. And this is going to create that window. So we calculate these two values out. This should give you 344.65, and this will give us 447.35. So if we put these together, this would give us our window. So we expect that an actual 60-year-old driver, we expect an actual 60-year-old driver to be able to read a sign from, and I'm just going to round these, from approximately 345 to 447 feet away. Okay, so hopefully that gives you an idea. Just think of standard error as the average error in our predictions, and we can use that to build that window of where we expect an actual person to fall based on the data. And this, of course, has, there's variability depending on how strong the relationship is. Well, that would be more confident, right? If this line was a really, really good fit for modeling the data, gave us a really good R value, R squared, then I would feel a lot more confident in my predictions on how accurate I think my predictions are, and even the window on that we're building to make those predictions.